Hello, this is a video entitled Phuket Word and Anthony Riley Can't Do Science. It's a bit quick and dirty, I'm afraid. It's in response to recent video posted by Anthony Riley on his channel, which I hate to publicize, but I need to for this. So first of all, I'd like to repeat the experiment that Phuket Word demonstrated in the video that Anthony has shown. So I've got a kitchen scale here and a 1 pound weight, and I'm just showing that the scale, it's not a very good scale, I'm afraid. I've got a much better one now. Records a 1 pound when you place the weight on it in air. Now we'll submerge the scales into a bucket of water, which is what Phuket Word did. He used a slightly different kind of scale. I make a little mistake here in that I put the weight on without first re-zeroing the scale, but never mind, it doesn't matter. I'll correct it in a second. So it's showing actually about 8 ounces there. It's very difficult to see here, but it's showing about 8 ounces, about half a pound rather than a whole pound. So obviously get a different reading. However, when I took the scale weight off, I noticed that the zero needle wasn't actually on zero because I put it into water, and it had obviously affected the scales and the movement. I then discovered that there was still an air bubble inside the mechanism of the scales, and the thing tried to float up. So we got rid of that and reset the needle to as close to zero as I could do. It's quite difficult to do this, but there we are. We're just about at zero now on the scale, and let's put the weight back in. There's the weight on the scale, and it's recording, I think it's about 13 ounces, 12 or 13 ounces, or thereabouts. It's clearly a different recording a different weight to the weight that was recorded when the whole apparatus was in air. And this is the basis of Phuket Word and Anthony Riley's claims that the density of the medium is the thing that matters. So let's consider what has actually been demonstrated here. We've seen that the weight of the 1 pound brass weight is a pound in air, and that the scales record a weight of about 12 or 13 ounces when the whole apparatus is submerged in water. Now, does this mean that the 1 pound weight now weighs 12 or 13 ounces because it is in water rather than in air? Or has it been shown that the scales are behaving differently because they have been submerged in water, and the weight is actually exactly the same as it was? So moving on, let's try and test this. Here is a bowl on a scale that's been zeroed and the same weight placed into the bowl, and it weighs 1 pound and 0.2 of an ounce. Now we will fill the bowl with water and then re-zero the scales. So the scales are reading 0, the bowl is full of water, and if we place the weight into the bowl, we record a weight of 1 pound and 0.2 of an ounce, exactly the same. Actually, it wasn't fully submerged, so you can see a little bit of air bubble popping out there. We'll put it back in, and we record 1 pound and 0.1 of an ounce. So perhaps 0.1 of an ounce difference, a tenth of an ounce difference between the weight that we record in air and the rate recorded in water. Given that the scales are actually rounding numbers up and down, I don't think 0.1 of an ounce is going to be significant in this. And we can say here that in this test, the weight is the same regardless of whether it is in air or it is in water. So the only sensible conclusion, having looked at these two experiments, is that when you place scales in water, they don't accurately measure the weight of the object that is placed upon them. This is something to do with the scales themselves and nothing to do with the object or with the medium that the object is in, because when we do that experiment, it remains the same. Okay, so let's summarize what we've observed. We've observed that the object's weight recorded in air is 1 pound and 0.2 ounces, and the object's weight recorded in water is 1 pound and 0.1 ounces. Small difference, which could be as little as 0.01 ounces because of the scales, the electronic scales are rounding up and down to record or to display the weight in a number of decimal places that are available on the display. And so the actual weight it's recording could be, or the difference could be as little as 0.01 ounces. However, it's either 0.1 ounce or it could be as little as 0.01 ounce, somewhere in that range. Now, it's a small difference, and it may be worth investigating if someone's that interested. Personally, I'm not that interested. I think it's probably due to the slight difference in the buoyancy of the weight in water and in air. So the weight, the brass weight will be slightly more buoyant in water than it is in air, and that the effect of that buoyancy force will be creating this slight difference in the weight that's recorded. I might be wrong. I don't really care whether I am or not. Essentially, for this particular object, the weight in water, the weight in air are identical. Now, when the scales themselves are placed in water and the weight of the object is measured, we get a value of 12 to 13 ounces. And this is significantly different to the weight recorded when the scales were in air. So that's a summary of our observations. What are the conclusions that we can draw? Well, in our experiment, the weight of the object is unaffected by the medium in which it is located. So water or air doesn't make any difference. We get essentially the same weight recorded. If the scales themselves are placed in water or air, we get a different reading. And so we can conclude that the scales do not accurately record the weight when placed in water. By definition, the scales are calibrated to be accurate in air. So if they give a different result when they're placed in water, then that result, it must be inaccurate by definition. Okay, so let's discuss what we've done. What reasons might there be for the scales giving an inaccurate reading when they're in water? Well, it could be a number of factors. In my opinion, the most likely major factor is the buoyancy force acting upon the scales or parts of the scales mechanism. And although the whole mechanism itself, when we consider it as one entity, is more dense than water and sinks, there will still be a buoyancy force acting upon all parts of the scales mechanism, and some parts of it are made of plastic which would float if placed into the water on their own. So quite a strong buoyancy force acting on some parts of the machine, and those parts are able to move within the mechanism of the machine. They're not held rigidly in place. If they were, then the scales wouldn't work. Yeah, they have to be allowed to move in order for the scales to operate. And so that buoyancy force that would cause them to float if they were on their own is acting on them as part of the machine and causing them to move within the mechanism, and causing the scales to perform somewhat differently to the way that they would perform in air. Because in air, the buoyancy force of those acting on those objects is considerably less than it is in water. Now, further experimentation could be carried out to test that hypothesis. For example, you might try and construct scales that were made entirely of heavy metallic objects and components. Although the buoyancy force, if they were the same size as the scales we used, if they were the same, if they were made of a heavier, a more dense material, a metal or something like that, the buoyancy force would be the same, but the gravitational force acting on those and pulling them down would be greater. And so the difference between the buoyancy force and the gravitational force on those objects would be greater, and perhaps the effect that the water would have on the performance of the scales would be reduced. And if it was a carefully designed instrument, you might be able to get that down to so that the scales actually performed absolutely accurately in water as well as accurately in air. There might be another way of doing it, would be perhaps to find some way of isolating the mechanism from the water. So the mechanism itself was in air, but you were able to measure the weight with the actual pan of the scales was in water, but everything else was not in water. And you might find that then the scales would perform absolutely accurately. And there might be a number of other experiments. These are just things that are occurring to me as I'm speaking. But further experimentations needed to test the hypothesis of whether it's the buoyancy force that's acting on the scales that's important here. But what is inescapable is the fact that the weight of the object is largely unaffected by the medium, whether it's weighed in a bowl of water or whether it's weighed in a bowl of air. Weight of that object is essentially the same. Now, that's not necessarily going to apply to all objects. Although I can show you another experiment that will show you that even a much lighter object will give exactly the same weight, whether it's in water or in this case floating on water or in air. So the effect of the buoyancy, if you like, on the object is largely irrelevant in the way that we're measuring the object here. So let's have a look at that experiment. So here we have another little experiment. This foam bowl placed onto the scales weighs or measures 1 ounce. So that gives us a nice reading of 1 ounce. Now if we place a bowl of water onto the scales, which weighs quite a lot, and reset the scales, recalibrate the scales to 0 and place the ball into the bowl, it again weighs 1 ounce. There's no difference whether that ball is placed in a bowl of water, floating on the surface of the water there, or placed directly onto the scales. It weighs 1 ounce. And if you put the ball back on and reset the scales to 0 here, which is a bit of a blunder, let's do that. Okay, reset them to 0 and place the ball on. It still weighs just 1 ounce. And just for completeness sake, I place the empty bowl on the scales and reset it to 0, place the ball in the bowl, and it weighs 1 ounce. So once again we see that placing an object in or on water doesn't make any difference to the weight that the scales record. As long as those scales themselves are in the air, then they will record the same weight. Now the measurement of weight is quite a complicated thing in some ways, and it would take a long time to go into all the details of how gravity, buoyancy, the difference between weight and pressure. What scales are often really measuring, particularly the electronic ones, is pressure, the amount of pressure that is being applied to the pad that is calibrated to record weight, and then that's converted to weight. Point is that the density of the object and the density of the medium are not really factors in measuring the weight of an object. The weight is a factor, or is a measurement of the gravitational force, and the mass of the object determines that gravitational force. In places where gravity is less, objects weigh less, and there's very simple experiments can be done to test this, but you do have to accept that we can travel to the moon and carry out simple experiments on the moon. I know we have done, and so does the rest of the planet. There's only a few crazy people on YouTube like Anthony and Phuket Word who think we can't go to the moon and measure things. So with that, I'll finish this video. Thank you.